Hello there. Today we are all about water polarity. And so before we jump into the instruction, I want you to take a look at these three pictures on the screen. And I think you'll recognize them. On the right, we've got a spider web, and then we see a picture of a couple of insects, three insects, water striders. And then down below, we see the hood of a car. And so what do you notice? What do you wonder about? What questions do you have? And does it remind you of anything else, any other places in nature where you've seen something that looks like this? So we're going to jump in here. And so our objective right now is this. Some atoms share electrons unevenly. And when they do that, we call that a polar molecule. It makes them polar. They have a charge, and that affects how they behave. And this is really important because we're made out of water. Water is essential to life. Water is on our planet. It goes through watersheds and travels all around the environment. And that polar nature of water really affects how water behaves. It's a big deal. So here's our skeleton of Cornell notes. Our essential question is, so what is a polar molecule and how are hydrogen bonds involved? And then how does this, we call it polarity, how does the polarity of water cause it to behave? So you can hit pause, write the skeleton of notes, and then fill them out as we go through the lesson here so you understand the material. The first thing I want you to look at is this. Here's a diagram or a model of a water molecule. And you can see we've got two hydrogens and one oxygen. And so remember, the atomic number of oxygen is 8. That means it has 8 protons, 8 positively charged particles that are all in the nucleus. For hydrogen, its atomic number is only 1, so it's got 1 proton in the nucleus. And so if you think about which one of those atoms has got a stronger positive force, it's going to be oxygen because it's got 8 protons versus hydrogen's 1. And so what that means is it's got a stronger positive force. And when these electrons are shared, you can see the electrons being shared here between the atoms. Oxygen, with its stronger positive force, is going to pull those electrons closer to it than hydrogen. So it's like a big brother and a little brother sharing something unequally. Think of it like that. But what it does is it leaves the oxygen side with a negative charge and the hydrogen side with a positive charge. That's what a polar molecule is. One side or one pole of the molecule has a positive charge, one pole has a negative charge. And now you can think of it like a magnet. It's not actually a magnet, but it behaves like a magnet. And so a demonstration you can do to see this is with this with this penny, and I've got a water dropper right here. And maybe you've done this in class. If you haven't, basically what we can do, I don't know if you can see this here, is we just keep putting drops of water on this penny. But if we look really carefully, we'll notice, 1, the water jiggles when I put a drop on it. And 2, it makes a pile. It doesn't spill over. It like bills and bulges. And so if you have something like this in your notebook already, you can add to it. If you don't, what I would do to describe what I would call that phenomena is phenomenal. Water is phenomenal. Here's what I wrote to describe the phenomenon. Water bulges on the penny. It actually makes like a dome shape. And if you look at this picture I have here, it actually, the water starts to hang over the sides. It's like defying gravity, which is pretty cool and pretty interesting. And so what we're going to do here is we're going to get into this cross-cutting concept called structure and function. What is it about the structure of the water molecule that allows it to do that? And so we're going to come back to this diagram later. And so I've got a model water molecule. There's a picture of it on the screen. And a couple things that I notice about just the picture on the screen is you can see, well, we've got the 2 hydrogens and an oxygen. And you can see that there's a plus sign there and a plus sign there by the hydrogens and a minus sign down here by the oxygen. That is the polar nature of water because of the uneven sharing of electrons. And I've got more water molecules. Oh, I don't want to spill. But check it out. And so they all stick together. They have something called cohesion. They want to stick together. But they're not super strong attractions, but they can keep moving around like that. And so what would happen if we did something like this, where we had the hydrogen or all the oxygens facing each other? Well, if you remember how magnets work, opposites attract, but the same charges don't. And so if you look here, we've got a negative charge and a negative charge and a negative charge. And if we tried to actually do that and make these things go together, what we find is that they don't want to do it. They repel. They don't stick. What does happen is they start to go together. Basically, oxygen goes with hydrogen, hydrogen goes with oxygen. And what we call that is a hydrogen bond. It's what we call an intermolecular bond. It's a weak bond between two molecules. And so go back to your notes and write that in. You can even draw a picture of it. And when that happens, we say that the word is cohesive. These molecules stick together. And then we can start to think about how that applies to this spider web. Those water molecules are like hanging on to each other. Or down here, if we can't walk on water because we break the hydrogen bonds. The bonds aren't that strong. But if you're a light enough insect, like a water strider, you can, we call that surface tension on the water. The insect's legs don't break the hydrogen bonds, and so it can just walk right across the water. How cool is that? Here's another diagram where you can just imagine, gazillions of water molecules all having hydrogen bonds together. Okay? And that leads us to another way water behaves. Not only does it cling together with cohesiveness, it also does something called capillary action. And I think this is really cool. If you think about how in the world does a tree like this get water up to the top leaves? It's something called capillary action, where you just got to picture these water molecules, like they're like a choo-choo train going up little vessels. This is called, this is like a little demo we could do in class where you can see, and maybe you've seen this in your life, where water is running up paper. Water not only clings to each other, it wants to cling to the sides of things. I've got some, I don't know if you can see this, but we've got some celery that I put in some colored water here. And just notice the color of the leaves. The celery sucks that water right up and it goes to the leaves. And basically, capillary action is when the water molecules are able to travel down a narrow tube or a vessel, like your blood vessels. You actually have blood vessels called capillaries. So let's go back here to our diagram. And so the function of all this, the way I would put it, is water is cohesive. Molecules stick together, and water is adhesive. Molecules stick to other things. It's because they have a charge. But here's what I want you to do. On your sheet, I want you to draw a model, draw a diagram that shows the water molecules and the hydrogen bonds on a penny that would represent this. And then here in this box, I want you to describe the picture that you just drew. And you can use words like negative charge, positive charge, electrons, unequal sharing, hydrogen bonds. But what you want to do is basically explain why water has this cohesive ability to stick together. Finally, we're going to bring you back to the note. Actually, I'm going to bring you to this thing here. And so we know, most of us know that water is and oil don't mix together. I've got a glass of water here. I've got some food coloring. And we see that the food coloring, I'm going to speed it up, the food coloring spreads out and mixes with the water. Here's the rule. Like mixes with like. And then when I put in oil, you can make a prediction in your mind. We see that the oil does not mix, right? It doesn't mix with it. And so our rule is like mixes with like things. Polar mixes with polar. Oil and grease are non-polar, so they don't mix. Okay, so back to the notes. So hopefully you can fill out that, and here's what I want you to do. For sure do this. I want you to write a summary that answers the essential question. I also want you to put a couple questions about the material there on the side. Okay, thank you for listening, and we're signing off for now. Write your summaries.